Today, we want to continue looking at line integrals. And we're going to be a little more careful about finding our potential functions. Yesterday, we just wanted an easy potential function to grab so that we could evaluate the line integral of a path-independent vector field using the fundamental theorem of calculus. Today, we want to take a function and come up with a system for how we can determine a potential function if there is one. Let's start with this example. We've got the vector field y cosine x times I and sine x plus y times j. So if there's a potential function, little f, for this vector field, then the partial derivative of the vector field with respect to x is y cosine x. So we have the partial of f with respect to x is y cosine x. So let's integrate this with respect to x. So that would mean that f would have to be y is constant. The integral of cosine is negative sine. So this would have to be negative, y is just a constant multiple, times the sine of x. Now we have to remember when we integrate, we get a constant of integration. But remember that this is a partial derivative. So our constant is not just going to be a constant. It could be a function of y. So what's happening here is that the constant of integration could be a function of y. So instead of just a constant, our constant could be some function of y. Because if the function is just of y, then it'll look like a constant with respect to x. So the constant of integration can be a function of y. So what we can do now is differentiate this expression for y and see if it gives us the df dy. So sorry, I got tripped up on something moving. I got squirreled. So the partial derivative of f with respect to y is sine x plus y. I also don't need this negative, do I? Integrating, not differentiating. You guys let me get away with way too much. So we've integrated the partial derivative of f with respect to x. With respect to x, we have this plus c1y. The new idea here is that the constant of integration can be a function of y only, instead of just a plain old constant. We know that our partial derivative of f with respect to y should look like sine x plus y, because that's the j component. Instead of integrating our partial of f with respect to y, we can just differentiate the expression we got from integrating the partial of f with respect to x. So let's differentiate f with respect to y and see if we land on the partial of f with respect to y. So what we're going to do is differentiate this expression well, let's differentiate this expression for f and match it to what we our partial of f with respect to y. So we'll see if it matches our partial of f with respect to y. So f is y sine x plus c1 of y. So the partial of f with respect to y, starting here, the derivative of y times sine of x, y is the variable, sine of x is just a constant. So the derivative of y to the first is 1, and we just get sine x plus the derivative of c1 of y now all we have to do is match the partial derivative of f with respect to y we get from the vector field and the partial derivative of f with respect to y that we got from integrating our potential function with our constant of integration. So what this tells us is that c1 prime of y must equal y. So putting those two together, we see that c1 prime of y must equal y. And since this is the derivative, that tells us that c1 of y is a half y squared. I'm not sure why I subscripted this one, or not subscript, but index. So our potential function looks like it must be y sine x plus 1/2 y squared plus some constants that's not going to be revealed by this process. The thing that we want to get from this example is that when we're integrating a partial derivative, our constant of integration can be a function of the other variable. Now that we've done this process on an example where it works, because we had a potential function, let's do this process on an example where it doesn't work. So let's suppose that we have a potential function and try to find it. If there's a potential function, then the partial derivative of f, the partial derivative of f with respect to x will be 2xy, and the partial derivative of f with respect to y will be xy. So we'll integrate our partial of f with respect to x with respect to x. So this will tell us that our f at xy is going to have to look like x squared y plus some function of y to be the constant of integration. Now we'll take the partial derivative of this function with respect to y and try to match it up with our partial of f with respect to y from the vector field. So the partial of f with respect to y is going to be x squared plus c prime of y and we're not going to be able to match this up. So our c prime of y has to be a function of y only, and we also need this x squared, and we don't have the x squared in our partial of f with respect to y. In the previous example, we took the partial of f with respect to y, and we had this factor, this term sine x, and so we have the sine x from the vector field. Here, we don't have an x squared in our partial of f with respect to y. The c prime of y has to be a function of y only. C of y has to be a function of y only. So c prime of y has to be a function of y only. This x squared might be plus c of x, the function of x only, but this c prime of y would have to be this xy, which is not a function of y only. So neither of these could be our xy. So neither of our terms in our df dy are x and y. Excuse me. So we can't have a potential function for this vector field. This vector field is not path independent. Any questions? All right. So this comparison of partial of, what we're comparing is the partial of the I component with respect to x. Sorry, the partial of the I component with respect to y with the partial of the j component with respect to x. And that's what's going on in this process. We're looking at the partial of the j component with respect to x and the partial of the f component with respect to I component with respect to y. I think this is definitely a more coffee problem. So we define this new thing. So let's just name the I and j components f1 and f2. If we look at the partial of f2 with respect to x minus the partial of f1 with respect to y, we'll define this the scalar curl, or the two-dimensional curl of the vector field. If the vector field is a gradient field, then the scalar curl will equal 0. If the vector field is a gradient field, then the scalar curl is equal to 0. What this means is that the partial of f2 with respect to x is equal to the partial of f1 with respect to y. And that means we'll have a potential function. So if the scalar curl is equal to 0, then the partial of f2 with respect to x is equal to the partial at f1 with respect to y. So that's the requirement for a potential function. So in our previous example, where we had the vector field forgot what it was already, 2xy I plus xy times j. f1 will be the 2xy, and f2 is xy. So the partial derivative of f1 with respect to y is 2x, and the partial derivative of f2 with respect to x is y. Since these are not equal, f is not a gradient field. Any questions? All right, so we've got this way of finding out if determining if a vector field is path independent. We got this scalar curl. Recall that we also know that a gradient field will have, if we calculate the line integral of a gradient field around a closed curve, we'll get 0. Got there in stages. So if we have a gradient function, a gradient field, and we calculate the line integral over a closed curve, since we just do f of q, the potential function at q minus f at p, if q and p are the same point, because we have a closed curve, then we'll get 0. So closed curve a closed curve just means that we end where we started. So here's one way to determine if we've got a gradient field. Calculate a line integral around any closed curve, see if you get 0. This curl is another way to determine if we've got a gradient field. And these two ideas are connected in a theorem called Green's theorem. So let's suppose that C is a piecewise smooth, simple closed curve. Closed just means the starting point is the ending point. Simple means that the path does not cross itself until the start meets the end. So the closed means the starting point and the ending point are the same. Simple means the path does not cross itself. So C is a piecewise smooth, simple closed curve that's the boundary of some region R in the plane. And oriented so that the region is on the left as we move around the curve. It's awful in words, but we've got this simple closed curve. So we've got some curve. And C is the boundary of a region R. And this oriented such that the region is on the left as we move around the curve is just saying, go counterclockwise. I should have emphasized the piecewise smooth part. So let's demolish a little bit of this. Let's have a point where it's not smooth. So even though this curve is not smooth at all the points, it's not smooth at these corners, it's smooth in pieces. And it's continuous. So it's not smooth at every single point, but it's smooth in pieces. That's the piecewise smooth part. So also suppose that F is a vector field on this region. The vector field doesn't contain C and R. The vector field just has to be smooth on a region containing C and R. So that there's something that we could fit on top, and the vector field is continuous there, or smooth there. Continuous derivatives. Then we finally get to write Green's theorem. Barely at the space for it. Then the line integral around the boundary of this region of this vector field dot dr is equal to, now I'm going to pause for a minute here because I just have this closed curve. That's something that we definitely use on line integrals. And then I just named the region that the curve contains. So I'll pause, give you an opportunity to think about what I could be possibly writing next. We're going to do a double integral over the region of the curl. So all this setup is just so that these integrals make sense. If we integrate a vector field around a simple closed curve, we'll get the same value as if we do a double integral of the curl on the region. And that's super cool. Right now, we're just writing stuff down, and you're like, oh, dude, what are you talking about? And you don't realize how cool this is just yet. So you put this out there, and people, should be, this is like a mic drop moment where I'm like, oh, check it out. And generally when this happens in Calc 3, for the most part, students like, oh, check what out? Like something big and dramatic was supposed to happen. All the instructors are always like, whoa. And the students are like, oh, what? And only later on do you look at this and say, whoa, that is pretty cool. This is kind of in the category of just look at the boundary type of integrals. Remember the fundamental theorem of calculus, we're integrating a function over an interval. Just evaluate the antiderivative at the boundary of the interval. When we were integrating a gradient field, just integrate the curve, just integrate the potential function at the endpoints. Just look at the boundary of the interval or the boundary of the curve. Now we're looking at this calculating a double integral of the scalar, double integral of the scalar curl of a vector field. We can evaluate the vector field around the boundary of the region. So in that sense, it fits in the what's going on the boundary type of integral. Any questions? Integration is a metaphor for life. Just take things a piece at a time. Break it into small pieces and deal with those. Things are changing continuously. Just assume that they'll be constant for a little while and deal with them simply. Then move on to the next thing. Make the continuous discrete so we can deal with it. Yeah, that'll give us, all we have is the consistency in the moment. And that's a good way to think about integration. I don't know how many of you have had to deal with a family member or a friend who has gone through memory problems, dementia or Alzheimer's later in life. But if you haven't, it's difficult. And it's difficult to find something that works. Because as soon as you find something that works, things change and you have to find something new. And the important thing to realize is that you're just integrating over time. You find a strategy that works for a little while, and then once that strategy stops working, after delta x is over, you just reevaluate and come up with a new strategy for the next delta x, because things are going to change. things are probably continuously changing, but your function can be constant for a little while. And there's a lot of things that work like that. We keep doing one thing until it stops working. Then we have to try something else. We have to reevaluate our function for the next delta x. Any questions? So that's Leach's life advice right there. It's in the form of integration. Reevaluate your function for the next delta x. That's not really going to be a successful life advice thing because it requires at least Calc 2. So there's not really a lot of people that are going to fall in line with this one. So I don't know. I don't know if that's going to be exactly successful. Which brings me to another interesting point. So I know a lot of you will probably think that you're kind of early on in your academic career. Some of you might be thinking that you're halfway through your academic career. Calc 3 typically happens at the end of your lower division work, your freshman and sophomore years in college. Or if you're me, your freshman, sophomore, and sophomore years in college. But as you're looking at this calculus stuff, think about what percentile of mathematical knowledge you're walking into. Don't have really hard numbers on this, but the place we could start is that I think it's safe to say that most people that are going to be well-versed in calculus have probably gone to college. Just that would be a hard number to find out. Actually, no, that'd be a hard number to find out because that would take a lot of effort. But for the most part, if you're taking calculus in high school, you're probably on a college prep track. You're probably going to go to college. Think about the number of people above the age of 25 who are old enough to have graduated college. Think about how many people have graduated college. Usually when I check, this is somewhere between 25 and 30% of people over the age of 25 have graduated college. Now, this is not all the people that have been to college. These are people that have graduated college. But then think about what portion of those majors, what portion of those people took majors where calculus was required. All you need to do is go to a college graduation and see and compare the sizes of the different schools if the college breaks things up into different schools. And you'll find out that not 100% of students that are graduating college have taken a calculus class. Or if they did, just took a calculus class so they could get through it. Maybe some of the engineers are in that category too. But my point is that the percentage of the population that's knowledgeable about calculus to the degree that you all are right now is pretty small. So welcome to the very small club. Scattered over a population, it's a very giant club. Proportionally, not so much. I wish we did get jackets. That would be pretty cool. At least like a pin or something like that. But anyway, you need to be in that to take Leach's life advice, which is assume that your function is constant and then reevaluate for the next delta x. All right. That's going to do it for today. that's going to do it for this week. Next week, we'll talk about more fundamental theorems. We'll look at more integral theorems that look at the boundary. And if I remember to, we'll talk about why this is called this quantity here is called the curl. Any questions? Think in terms of directions. The partial of f2 in the x direction, partial of f1 in the y direction. It's a combination of horizontal and vertical stuff. It's how things are swirling around. All right. That's going to do it for today. That's going to do it for this week. I'll see you all on Monday. Everybody have a good weekend. I think those should go in the other order. Have a good weekend. I'll see you on Monday. And thanks for playing. Yeah, that much better. That's much better.
Thanks, Professor.
Have a good weekend. I'll see you all on Monday. Thanks for playing.